So, good morning students, welcome back to chemistry class. In the last previous lecture, that is lecture 14, students, I discussed with you very importantly what? The rules controlling electronic configuration of elements, right? Rules controlling what? Electronic configuration of elements. So what are those? First one, Aufbau principle. Then second one, N plus L rule, that is lowest sum rule, which is also called as Bohr's-Bury's rule. Okay. Then I told you Pauli's exclusion principle, third rule. Then fourth one, Hund's rule of maximum multiplicity. Right? Just once again I will give the statement of those. As I told you yesterday, Aufbau is a German word. In Indian meaning, its meaning is to build up. What you are building up here, students? Electronic configuration of elements. Okay. So, accordingly it is stated as electrons enter into the various orbitals, like from 1s to 8s. How? According to their increasing energy levels. Is that what I given you? Yesterday with the help of Molar's diagram, 1s, 2s, 2p, 3s, 3p, 4s, 3d, okay, 4p, like this it will continue up to 8s. Right. Then second question arises, sir, how to come to know that which orbital is having less and more energy? For that I told you that use N plus L rule. N plus L rule will help us in comparing energy between the orbitals, whether 2p is having less energy or 3s is having less energy. I told you there are two rules. If the sum of N plus L rule found to be different, okay, then N plus L value which is having more, that orbital is having more energy. And N plus L, which orbital is having less value, that will be having less energy. And according to Aufbau principle, always electron enter into lowest possible than to highest possible. Right? Okay, then if the N plus L value after adding comes to be same, they are called as degenerate orbitals. Orbitals having same energy or identical energy. In that case, second rule you have to follow. What is that? In case of degenerate orbitals, if the value of N plus L is same, then the orbital with higher value of N, small n, that is principal quantum number N, that will be having more energy. Right? Okay, this is how we have discussed Aufbau principle and N plus L. Then third one, Pauli's exclusion principle. No two electrons of an element can have the values of all the quantum numbers same. They may be same with respect to, that is principal quantum number, azimuthal quantum number, magnetic quantum number, but they differ in spin quantum number. Okay, right. Then next, I told you lastly, Hund's rule of maximum multiplicity. So what does the Hund's rule states? Hund's rule tells us about clearly regarding pairing of electrons. Okay, as I told you, in case of degenerate orbitals, that is orbitals having same energy, how electron enter? First they occupy singly, then pairing of electrons start. Right? As I given you example from boron to neon. Okay, in boron it will occupy first singly 2px1, then carbon 2px2, then nitrogen 2px3. Then pairing start from oxygen, okay, 2px2, 2py1, 2pz1. Then for fluorine 2px2, 2py2, 2pz1. And lastly neon 2px2, 2py2, 2pz2. Like this pairing starts singly unless and until they are singly occupied. And remember students, always electron entering upward, clockwise and then downward. Okay, this is about Hund's rule. And lastly another importance I forgot to tell you. Next one I told you, just I will continue in the next lecture, that is only 50. Significance, see, half-filled orbitals, lastly. Significance of Hund's rule. Okay, what is the significance? Very importantly, according to Hund's rule, half-filled orbitals, okay, and completely filled orbitals. Completely filled orbitals. Completely filled orbitals gain extra stability. Gain extra stability. See, students, you are always under impression that only completely filled orbitals are what they are stable, but actually not like that. Even half filled orbitals are also stable. That too extra stable. How? Let us see with some examples. Now you already know completely filled orbitals they gain extra stability due to what? Symmetric arrangement of electrons, symmetric distribution of electrons. Second point. See, completely filled orbitals. Completely filled orbitals. Completely filled orbitals gain extra stability. Extra stability due to what? Extra stability due to symmetric distribution. Symmetric distribution of electrons. Remember, symmetric distribution of electrons. For example, just you can see in 2p orbital, right? 2px1, 2py1, 2pz1 according to Hund's rule strictly first, okay? Then you see here symmetric arrangement, and this is symmetric arrangement. This is called symmetric distribution of electrons. That means they are all paired, right? Okay, this is the first case. Then how are half-filled orbitals they gain extra stability? This is the important. Half-filled orbitals they gain extra stability due to what? One of the another important concept called as exchange energy. Exchange energy. What is that exchange energy? Let us will understand with the example. Okay, right. What is that exchange energy? So this is completely filled orbital. They gain extra stability. But see, half-filled orbitals. Half-filled orbitals gain extra stability. Due to exchange energy. Within the same subshell. Remember, within the same subshell. Okay, let's see. Due to exchange energy within the same subshell. Point to be noted. Very, very important for CET as well as for NEET purpose. So that's why I not make yesterday's class. Okay. That means by writing electronic configuration, if they observe this symmetric arrangement, they are almost stable due to this symmetric distribution. But half-filled orbitals due to exchange energy. Let us explain you with one example. Okay. What is that example? Just I will share with you here. Okay. Okay, this is what I have shown you. Completely filled orbital. Now half-filled orbital in this case, just observe here students. Suppose if it is 2p same orbital only. All are half-filled, that is nitrogen. Right? This is for 2p. Like this. For d orbitals, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? Okay. Like that for f orbital, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Right? So d5, this is p3, and this is the f7. Right? So d5, all are half filled, and the f capacity also half filled. Remember, right? Okay. Now, which is more stable? F7 is more stable. Why? More unpaired electrons. More exchanges, Why? Because for exchanging they lose energy within the same subcell to get pair up. That decrease in energy to pair up within the same subcell is called exchange energy, right? So number of exchanges for p orbital here. So you see number of exchanges for p orbital. See, this electron can exchange with this and here. 2 exchanges. But this electron can exchange 1, 2, okay, 3 and even 4. 4 exchanges. Like this one, 1, 2, 3, right? 4, 5 and 6. Like this. Number of exchanges for this one, see, 3 into 2, okay, divided by 2, that is 6 by 2, that means 3. Here, number of exchanges, that is 1, 2, 3, 4, total 5 into 4 by 2, that is 20 by 2, right, that is 10. And lastly for this one, 7 into 6 by 2, that is 42 by 2, 21 exchanges. So these are the possibilities of exchanges, see, right? As number of exchanges increases, energy decreases, stability increases. So this is the significance of Hund's rule of maximum multiplicity. Okay, I will repeat. Filled orbital, they gain extra stability due to what? Exchange of electrons within the same subcell. Exchange of electrons within the same subcell. During their exchanges, that is, with these 2 other orbitals, they lose energy. That decrease in energy during the exchange of electrons within the same subcell is called exchange energy. As the number of exchanges, probability of exchanges increases, energy decreases and stability increases. That's why half-filled orbital they gain extra stability due to exchange energy, whereas completely filled orbital they gain extra stability due to symmetric distribution of electrons. Please try to remember these, students. Okay. Suppose you are asked which is more stable, nitrogen or oxygen. Accordingly, nitrogen. Why? 3 unpaired electrons, whereas oxygen only 2 unpaired electrons. Like this, in theory or in CET they may ask you on the comparing the stability in increasing order and in the decreasing order. So that's about the stability, right? Okay. That this is the last significance of Hund's rule of maximum multiplicity. Right? So lastly just we will end. What is exchange energy, students? Point to be noted. What is exchange energy? Exchange energy. I repeat, exchange energy. What is exchange energy? Exchange energy is nothing but the decrease in energy. Decrease in energy. When the decrease in energy when electrons exchange within themselves within the same subshell. Okay, within the same subshell. The decrease in energy when electrons exchange within the same subshell is called exchange energy. Okay, exchange energy. As the number of exchanges increases, I repeatedly told you, students. Okay, the energy decreases, stability increases. Please remember. This is lastly regarding what significance of Hund's rule of maximum multiplicity. Lastly, the word multiplicity indicates what? Number of unpaired electrons, students. Okay. If the number of unpaired electrons is 1, it is called singlet. 2, doublet. 3, triplet. 4, that is quartet. 5, pentet. 6, hexet. 7, that is heptet. Maximum will have only 7. Why? Because 1s orbital, 3p orbitals, 5d orbitals and 7f orbitals. Like this you can remember. The word multiplicity, remember, it is unpaired electrons in the valence shell of an atom. right? Okay. Now this is regarding all. Another complete detailed information regarding the Hund's rule of maximum multiplicity, right? And this rule exclusively tells you about what? Pairing of electrons in the degenerate orbitals, that is orbitals having same energy, identical energy or equal energy. As I told you yesterday, what are the examples? One s orbital, no, it is not a degenerate. P orbital, d orbitals and f orbital can give px, py, pz, then dx square minus y square, dz square, dxy, dyz, dzx, yz, like this 7f orbitals. They are example of degenerate orbitals. Okay, right. Now last theory part regarding this usually. Okay, after understanding the rules controlling electronic configuration, I will take you to the next. What is a node? What is node? And what are the types of node and how to predict the number of nodes in the orbitals? Okay. Next word is what? Node. Remember the word node. What is first node? See, node is nothing but it is the three-dimensional region. Okay, the three-dimensional region where probability of finding electron. Probability of finding electron is zero, not maximum, is zero around the nucleus. Or the space around the nucleus where probability of finding electron is zero. That is also we can tell. Okay. A three-dimensional region where or space around the nucleus where probability of finding electron is zero. Let us go in that manner only. The space around the nucleus. The space around the nucleus where probability of finding probability of finding electron is zero. This is where that is around the nucleus. The space around the nucleus where probability of finding electron is zero is called nucleus is zero around the zero is called node. Okay, right. Now we come to the types of nodes. See, there are basically two types of nodes. Just I will tell you with the example. What are those? Radial nodes or spherical nodes. Remember here, radial nodes are spherical nodes. You are observing here, radial node is also called spherical node because it is spherical in the shape. You are observing here. See, this is a shape of electron cloud picture of 2s orbital, right? See, we are observing here. This is all shaded space is called electron cloud, and you are observing here empty space. This empty space around the nucleus, that space is referred to as what? Node. So nodes are of two types. That is one radial or spherical, which are always associated with what? S orbitals. Whether it be 1s, 2s, 3s up to 8s. Okay. Whereas angular nodes. Okay. Angular nodes. Remember, radial or spherical, don't confuse, and angular is totally different. Angular nodes are only for P, D and F orbitals. P, D and F orbitals, they are having angular nodes, whereas S orbital, they are having exclusively spherical or radial nodes. And the probability of finding electron zero around the nucleus or space around the nucleus where probability finding electron is zero, is called node. Node may be spherical or radial, that is only s orbitals, and node may be, that is angular, especially p, d and f orbitals. Okay. In P, Px, Py, Pz. In D, x square minus y square, z square, xy, yz, zx. Like that. F orbitals, you already know, they are highly complicated. Like that. See, I will show you with the pictorial representation. Please see here very carefully. This is best example for what? Radial or spherical nodes only given by s orbital. See, you are observing. Spherical. Okay, not oval. It is spherical. Right. Next, see, angular node. See. This is the symmetrical distribution. See, distribution of a dumbbell shape. You know that p orbitals are dumbbell along the x-axis, right? Now what you are observing, this is y and this is z. What you are observing in three-dimensional is a dotted space. That is called as what? This is called nodal plane. Okay. Yes, orbital do not have nodal plane because all along x-axis, y-axis, z-axis, the whole spherical electron will revolve. But this is not like that. Dumbbell shape, if it is px, only along x-axis. If it is py, only along y-axis. If it is pz, only along z-axis. Right? And they are perpendicular to each other, remember. That's why, see, this is angular node in the p orbitals. Remember. That means basically how many types of nodes, students? That is spherical or radial. Don't confuse. Spherical and radial, they are one and same, only s orbitals. Whereas angular nodes, purely they are perpendicular to each other in three-dimensional region. What are those? P, D and F orbitals. Okay. Right. Now lastly, with this diagram you have completed, right? And that is clearly understood what is a node and what are the types of a. Okay. Now lastly, one more point, especially for theory as well as CET, point to be noted, that is the number of nodes. See, only I am telling you nodes in an orbital. In an orbital is given by what it is? N minus 1. Principal quantum number minus 1. Please try to remember this. Okay? N minus 1. Whereas, this is the first one. Then second, number of nodes. Okay. So number of, that is radial or spherical. Spherical nodes is given by, that is n minus L minus 1. Please remember this. Principal quantum number minus azimuthal quantum number minus 1. Suppose if they ask you number of angular nodes, it is only n. Remember, here these formulas you have to compulsorily remember for CET and for theory, right? Especially for CET and NEET, right? Right. So that's about the formulas to remember, calculate. Suppose it has to only nodes, it is n minus 1. The radial nodes, it is n minus L minus 1, and it is angular nodes, it is only L. Okay, right. Just I will give you 1-2 examples. Suppose if you are asked, for example, how many that is radial and angular nodes are there in 1s, 2s, 2p orbitals. Suppose these are the orbitals. Okay, 1s, 2s and 2p. Then you should be able to tell one by one. First let us take first one, 1s. 1s. See, radial nodes. Radial nodes is what is the formula, students? N minus L minus 1. Right, very simple. That is n value. See, this is the 1. 1 minus. What is the value of s orbital for L? 0. And this is 1. Right? So radial nodes for 1s orbital. 1s orbital is how much it is? 1 minus L value is 0 and this is 1, this is 0. Right? 0 radial nodes. Okay, then even angular nodes is L. Angular nodes is L. That is L means that is also 0. Because for s orbital L value is 0. So like this you can go for 1s, there is only 1 that is spherical, that too L is equal to 0, that itself is what? L 0 means what? S orbital, only 1 orientation, right? Okay, this is for 1s. Like this for 2s. If you go for 2s now, like the same, radial nodes, n value, 2. L value once again for s orbital 0, 1, and here we will have 1. For 2s there is one radial node or spherical node, and angular node is what? Once again 0. There are no angular nodes in s orbital, already I told you. Okay, then coming to next 2p. This is important, 2p. When you calculate for 2p, radial nodes, as it is given by n minus L minus 1. N value 2, L value for p orbital is 1, and this is 1. 2 minus 0. L value is 2, see here. L value is 2. Sorry, L value is 1 for p orbital, that means for 2p orbital is having 1 angular node and 0 spherical nodes or radial nodes. So, but in general, total number of nodes, suppose if they ask you, in nodes in 4s orbital, then you can use formula n minus 1. What is the value of n? This is the first principal quantum number, 4. Okay, minus, that is 1, will be 3. Only nodes. Suppose if it is 4p, also same, that is n, 4 minus 1 will be 3. Right? Okay, so like this you can go for number of nodes in a particular orbital. Right? Okay, see once again repeat, say number of nodes in orbital is n minus 1, whereas number of radial or spherical nodes is n minus L minus 1, and angular nodes is, that is, yeah, so don't get confused. This is all about regarding nodes and nodal planes. Right? See, node is a what? Is a space around the nucleus where probability of finding electron is 0. Right? Whereas nodal plane, or what we call it as, there is no nodal plane for s orbital because it is circulating all around x-axis, y-axis, z-axis in a spherical way. That's why we call it as node. But when you come to p, d, f, px, py, pz, dx square minus y square, dxy, dyz, dzx, dz square, they are orienting in some x-axis, y-axis, z-axis, right? That's why that is therefore nodal plane, right? So only s orbitals, they are having spherical or radial nodes, which is n minus L minus 1, whereas p, d, f, they are having angular nodes, which is nothing but L. But number of nodes in any orbital is n minus 1. So that's about regarding the nodes. So students, almost all see, we have covered regarding electronic configuration, rules controlling electronic configuration, right? Then one, that is significance of Hund's rule. I told you, half filled orbitals and how completely filled orbital they gain extra stability, right? So finally now we'll come to last part of this atomic structure chapter, that is called electronic configuration of elements. Okay, electronic configuration. Electronic configuration of elements. Okay, students. The first question arises, what is electronic configuration? Already you have studied, since you are studying from high school. Okay, since you are studying high school, right? Electronic configuration. Kannadalli ಏನಂತಾರೆ? electronic vinyasa, right? What is electronic configuration? It is the arrangement of electrons in various orbitals according to their increasing energy levels. Almost like that at the what? Aufbau principle. Okay. That's why I told you rules controlling electronic configuration. See, the same statement is repeating here. What is electronic configuration? The arrangement of, definition is the arrangement or distribution of electrons. Okay, arrangement or distribution of electrons in various orbitals according to their increasing energy levels. It's called electronic configuration. Okay, electronic configuration of elements. Right, this is the definition you already know. The next question arises, students, what is the significance and what is the importance of writing electronic configuration? Why you have to study this? Simple. See, stepwise just I will write. By studying electronic configuration, students, you come to know valence electron mainly. Means outermost electrons in the valence shell, outermost orbit. Okay. Then with the help of that you can write general electronic configuration of elements. General electronic configuration of S, P, D and F block elements. Not only that, even you come to know the chemical property, mainly it indicates a chemical property of an element. And also you will come to know what oxidation state, primary as well as even variable oxidation state, right? These are all information you will get by writing electronic configuration of elements. Even I told you how many unpaired electrons are there, that is nothing but multiplicity using Hund's rule. That also you will come to know. These are all information you will get by writing what? Electronic configuration of elements, students. Right, now just I will write what is the significance by writing, right, electronic configuration of elements. It helps us to know what first regarding valence electrons in an element. Okay, first one. Then not only that, even you know the chemical properties. It will decide the chemical properties of elements, not physical, mainly chemical properties. The chemical properties decided by what? Electronic configuration, valence electrons, right? And even oxidation state of element. Not only oxidation state of element, even students, you can also know group valency and group number. Because see, we are writing electronic configuration on the basis of what? According to modern periodic table as given by Moseley, elements are arranged in the periodic table according to what? They are periodic functions of their atomic number, not atomic mass. So here in electronic configuration we are writing the elements according to their increasing energy levels based on atomic number. So that will decide what? Chemical property of element mainly. This is most important point to be noted. Then valence electron, no doubt. Oxidation state, primary as well as variable, and even group valency and group number. So many all other characteristics you will come to know by writing electronic configuration. And even I told you, even in deriving general electronic configuration of S block, P block, D block and F block elements. So this is the significance of writing electronic configuration of elements. Okay. So students, this is class. Just see what we have discussed is today's. See, yesterday I completed what rules controlling electronic configuration of elements. Okay. Right now it's a turn of after understanding once again last bit, that is what half filled orbitals and completely filled orbitals gain extra stability. Why? One due to exchange energy and one due to symmetric distribution of electrons. Right? And then lastly, just given you this particular nodes. What is a node? It is the space around nucleus where probability of finding electron is zero. It may be a radial node or it may be angular node. If it is radial, that is spherical, only for s orbital. If it is angular, only for p, d and f. P, d, f, they don't have radial nodes, only they have angular nodes, whereas s orbital only radial, no angular nodes. Please remember. So number of nodes in any orbital is n minus 1. Radial nodes n minus l minus 1. Angular nodes only l. Please remember this. Right. And just lastly, I am concluding this with this definition of electronic configuration and its significance. Okay. So I think today we will stop here. So until tomorrow's class, that is in the lecture 16, lastly we will complete writing electronic configuration of elements. An electronic configuration of elements from atomic number 1 to atomic number 36, at the maximum we will go for 54. Okay, where I will tell you how to apply the rules of Bohr principle, Pauli's exclusion principle. Even very importantly, Hund's rule help you very much in filling electrons. Okay, that is in the box. Okay, that is block diagram electronic configuration. And also I will try to tell you how to identify unpaired electrons, variable oxidation state when you come to D block elements. Right? So today we will stop here. So enjoy the days. Thank you.